as I said, we're looking towards our exam on November 2nd. I'm not sure if I mentioned this, but we will have some extra credit opportunity coming up soon. You're going to have a couple of different things. First, we're going to have, hey Zane, going to have a food drive coming up beginning at the end of this month. Y'all might be familiar with Nickel Scan. Is that right? You've heard of Nickel Scan before if you've been here for more than a year. Uh, so we'll be participating in that food drive. It's going to be all of my classes together, and I'll ask you to bring in maybe a couple of items. And when our classes reach the goal, then all the classes will get probably 10 points of extra credit. That'll go towards your exam scores. Basically, I have a big pot that I put all the points into, and then I calculate the average from all those scores. And then also at the end of the semester, we'll take an assessment. Actually, prior to the end of the semester, we'll take a general education assessment. Might wait until the final to take that assessment. That way you'll be prepared because it will be cumulative just like the final. And that assessment will also be worth 10 points. Okay. But for the food drive, everybody in all the classes will get that extra credit. For the assessment extra credit, you'll get whatever percentage you get correct on that assessment of those 10 points. Is that clear what I mean? So you have the opportunity for 20 extra credit points, but you'll definitely get 10 if we meet our goal as a class for the food drive, and then we'll get some percentage of the remaining 10. If you get 80% on the assessment, it's to be a multiple choice test. Then you'll get 8 points of extra credit. Quite clear on what I mean by that? The extra credit can help you, but I think we have like 600 points. So I mean, you can do the math. 20 divided by 600, what's that? 2 over 60. It's less than, or it's right about 1.5 percentage points. So if you're at an 88, then it'll bump you up to an A. But if you're at say a 95, it's not going to help you. Or if you're at an 85, it's not going to help you. Okay, so it'll help some of you, but not all of you. My point is, don't rest too much on that. But if you've done poorly on the first exam, it can help you because it is 20 points. Any questions about that? What I mean? No? All right. Let's see. Let's pick up here. Actually, I accidentally put the answers in on these, but I'm going to give you some different questions based on this figure and see if you can answer them. I'm going to give you some expressions for the dot product of the work, and I want you to tell me which of these scenarios fits the expression. So each of these blocks is moving to the left in that direction, and so actually, let's make this to the right, so we make that displacement positive. So each of these is moving to the right. And now I'm going to write an expression for work. It's going to be, let's say, 2 newtons in the I direction, dotted with 3 meters in the I direction. And I want you to tell me which one of these represents that expression. 2 newtons in the I direction, dotted with the dot product of those two vectors, where the displacement is 3 meters in the I direction. And remember, our work is equal to F dot D. Both of these are vector quantities, but our work is a scalar quantity. So this expression fits which of these figures, A, B, C, or D? Go ahead and answer that one. And I'm going to write a different one. Right now we're looking at the top one in blue. Which scenario does this function represent, or does this dot product represent? Is it A, B, C, or D? Or if none of them, you can put E. Right now we're looking at this one. What's this? Is that a problem, that big black line down the middle of the screen? Okay, I'm sorry, I didn't think about it. All right, let's stop at 122. Okay, let's see. C is the right answer. And what I'm looking at here is that the force is in the I direction. C has the force in the I direction. The displacement is also in the I direction. Is this force doing positive, negative, or zero work? Positive work, because I have 2 times 3. It's actually doing 6 joules of positive work. What about this next one? Let's look at the one in red here. And while you're doing that one, I'm going to go ahead and write a third one. All right, let's stop at 40. Okay, awesome. B is right. It's doing, or it is matched up with option B here because my force is negative, my displacement is positive. Is that one doing positive or negative work? Positive or negative? It's doing negative work. In fact, it is doing negative 12 joules of negative work. When I talk about doing negative work, I mentioned this last time, the negative doesn't give direction, right? The negative says what about the work? That the work is doing what? Okay, yeah, it's the opposite of friction, sorta. Not really, but what do you say, Brennan? It's removing energy. So when I have a negative in the work, it's a scalar quantity, so it doesn't have a direction. What that negative means is that it's taking away energy, like friction, Asia. So friction takes away energy, so it does negative work. Let's do this last one. Oh, what is Mozart doing right now? Right now. Decomposing. Okay, now let's do the one in green. I have negative 2 newtons in the I direction plus 2 newtons in the J direction, dotted with 2 meter in the I direction. Oop. Right, let's stop at 30. Stop at 30. I got the hang of this, sort of. Stopping at 30. Okay, so D is the right answer. And I'm looking at it as my force vector. I have negative 2I plus 2J. That's this vector. This has a negative X component, a positive Y component. I can draw the components of that vector. It's going to look like this. This is the X component. This is the Y component. And then I dot it with my displacement vector, which I give right here. Remember, when I do the dot product, I only take like terms. So the work that's being done by this force is going to be what? What will be the work? This force, negative 2I plus 2J, dotted with 2I, is going to do what amount of work? Negative 4. That's right, because I don't multiply these two terms because J dot I, two perpendicular vectors, would equal to 0. Anytime I take the dot product of two perpendicular vectors, the product of those two is going to be equal to 0. I dot I, on the other hand, is equal to 1. So the work done by this is equal to negative 4 joules. That means that since my object is moving in this direction, so something is pulling it in this direction, that means that this force is taking away from the energy. I have one force pulling in this direction, and then I have another force, Fx, pulling in this direction. That means that this force is a dissipative force. It's taking energy away from the motion of that object, or from that object, and it's taking it away this amount. It's taking away negative 4 joules of energy. Okay, so when you lift an object, do you do positive or negative work? Let's do this as a clicker question. Do you do A, positive, or do you do B, negative work? When I take an object and I lift it up from the ground, am I doing positive or negative work? the force that I apply to the object, is that positive or negative work? Hey, Tyler? Okay, I'm going to stop at 30. Okay, awesome. A is right. I have an object. I apply a force in this direction. My displacement is also in that direction. Work is equal to F in the J direction, dotted with the displacement also in the J direction. And so that is going to be positive the magnitude of F times the magnitude of D. But it's positive because they're both in the same direction. Josh, you have a question? Yes. No, it wouldn't be negative. Josh asked, if I have a pulley, and in your engineering classes you'll get into these more, but if I have a pulley and I'm applying a force in this direction, um, really this force is transferred over here directly. So this force is the same as this force. So pulleys are simple machines, and they can do a variety of things, but primarily they change the direction of the force. So when you use a pulley, you've changed the direction of the force. You don't need to know this for us, but yeah, you're engineering. You'll have classes you talk about this more, probably in your dynamics class. Okay. Does gravity here, if I'm lifting an object, does it do positive or negative work? Just tell me. Does gravity do positive or negative work? If I'm taking an object and I'm lifting it, does gravity do positive or negative work? I want to think about what is the displacement and then what is the direction of the force. The gravitational force is up or down? It's down. Your displacement is up. So is that a positive or negative amount of work? Negative, right. So I have one force that's doing positive work here, and then I have another force, the gravitational force. I'll call that FW. FW, because it is opposite the displacement, does negative work. Because I have work equals the force weight, this is in the negative J direction, dotted with the displacement, which is in the positive J direction. And so this is going to be negative FD, uh, negative F times D, where F is FW. So I have one force that does positive work and one force that does negative work. If I want to know the total work, that is going to be equal to the work done by F plus the work done by FW. We'll work some problems as we get into this, and then we'll actually do some calculus problems where we're integrating the total amount of work that's done. Because remember, an integral is really just a what type of thing. If we're derivatives are finding the slope, integrals are finding the what? Not the average, no. Okay, yeah, that's another word, but we talked about this in chapter 2, right? When we take the derivative of a function, we find the slope. When we take the integral of a function, we're finding the, yeah, we did, when we had a v versus t graph, we were finding the displacement. But do you remember the integral? We were finding not the slope of a function, but the, what, under the curve? The area, right. So an integral, you can also think of it as a summation, as we're finding the area under a curve and we're summing up all those parts underneath the curve. So we'll see integrals later in this chapter, because what we're going to do is we're just going to add up a bunch of different terms. But the total work here is the sum of all the individual works done by the individual forces. Don't worry, we'll get into that more. We'll do some practice problems for that. Okay, let's just try this quick test. This is a good simple one. I just want to know the work. I have this shopper that's pushing a cart with a force of 40 newtons, directed at an angle of 60 degrees downward from the horizontal. And I want to know the work done by the shopper as she moves down a 25-meter aisle. force in this direction, 60 degrees, down a displacement in that direction. What is the work done by the chopper? Don't try to think too much about this one. We have an expression for work. I'm just asking you to pick out the right numbers and calculate the work being done. All right, we'll do about 10 more seconds. Stop at 150. 150. Okay, awesome. B is right. Again, don't want to think too much about it. I have a force, I have a displacement, I have an angle between them two. That's FD cosine theta. F is 40 newtons. Our distance is 25 meters. Now, if the 40 newtons was in the same direction as the displacement, then this would be the end of it. But I want to find the component of the force that's in the same direction as that displacement. And the component of that force would be Fx, and it would be in that direction. In order to get the component of that force, I have to multiply times that angle cosine of 60. And let's see, that's 800 cosine 60. What was the answer? Okay, yeah. So the answer is B. Not 800, 1,000 times cosine 60. Cosine 60 is a half, so that's 500 joules. I'm doing 500 joules of work on this object. Right? Now, we're going to see that that work is all converted into energy, and that's going to come into our work energy theorem, that whenever I do work on an object, I increase its energy. If I do negative work on an object, I take away its energy. When we say that, we're saying the work energy theorem. If I do work, I change the energy of an object. If I do work, I change the energy. If I do positive work, I add energy. If I do negative work, I take away energy. So kinetic energy, let's first talk about kinetic energy. We talked about it a little bit, but kinetic energy is the energy of a moving particle. Whether it's an alpha particle that you get from radiation, or electron, or a gas molecule. In fact, you chemistry majors in your thermal physics or your thermal chemistry class in PChem, you'll derive actually the energy of an ideal gas based on the motions of a gas molecule as they move through space. But our kinetic energy is equal to 1/2 mv squared. Notice a couple of things here, that our kinetic energy is proportional. Actually, we're going to use just a K for kinetic energy. Sometimes you see it as KE, and I'll probably go back and forth, but I'm going to use K for kinetic energy. Notice that our kinetic energy is proportional to V squared. So, for example, if I double this value, that means I'm going to quadruple my kinetic energy. Whereas if I double my mass, I only double the kinetic energy. You follow what I'm saying? I have this quadratic relationship between the kinetic energy and the speed of the object. Also notice that even if you consider this variable is the speed, and even if you consider this variable to be the velocity, notice that when you square it, that any velocity information is stripped from that value. Because if I square a negative number, it becomes a positive number. So kinetic energy is scalar, and has no directional information. Also, I was about to say something. I forgot what I was going to say. I don't remember. It'll come up soon, I think. But the unit for kinetic energy is the joule. It's the same as the unit for work. The unit for kinetic energy is the joule. If I do work on an object, I change its energy. This is why sometimes in other books you might see, I mentioned this to you, but that you might see the unit for work being a Newton meter instead of a joule, but really they're the same. If I do work on an object, I change its energy. So we'll use joule for both kinetic energy and for work. Uh, Back in the 1700s, they used to think that the kinetic energy was proportional to the speed of an object and not the speed squared. And the reason for this was it was sort of superstitious that they believed that squared numbers were demonic in some way. I mean, you might think squared numbers are demonic too, but we know that that's not the case. That if I multiply a number times itself, then there's nothing really supernatural in that. But back in the 1700s, they thought that. Which is right, because, in the 1700s, people used a lot of squared numbers, even just normal people. Do you know why they would use squared numbers in, say, the 1700s? What did people do primarily? Most people, what did they do during that time? They did farming, right? So, because it's a very agrarian society, you either raise crops to sell to other people, or a lot of people just raise crops just to live because they didn't have the same food supply that we have. And so, why would a farmer want to use squared numbers? Well, a farmer, he or she has fields that they want to plant, and so they need to figure out what is the amount of seed that they need to plant. And so they have to know the area of the field. There's a lot of area calculations, which require squared numbers. So anyway, that's sort of an aside, but that was part of the reason why they thought that kinetic energy was proportional to the speed. And then there was a lady, which was unique in the sense that there just weren't that many women in science at the time. And also, most scientists were really wealthy. It turned out she was pretty wealthy too. But she did an experiment where she took some clay and she dropped a ball. She dropped a steel ball. And she dropped it such that when it fell onto the clay, it had a speed v. They knew the same equations of motion that you guys know now. So she knew from what height to drop it in order to give it a certain speed v. And then she measured the indention that the ball made into the clay. Say it went down, I don't know, a distance d. And then she dropped the ball from a bigger height so that when it dropped onto the clay, it would have twice the velocity. Now, the depth of our hole here is going to be proportional to the amount of energy, directly proportional. So the amount of energy is directly proportional to d. So if I double the velocity by what they think that the kinetic energy is proportional to v, by how much should the ball have made an indention? How much deeper should have this indention been if, in fact, kinetic energy was proportional to v? What did they expect to happen? It would just be twice as deep. But of course, that's not what she found. She found that the hole was how much deeper? 4 times as deep. Because by increasing the speed by a factor of 2, she gives it a kinetic energy that's greater by a factor of 4. So this is not true. Instead, the kinetic energy is proportional to v squared. And when she doubled the speed, she quadrupled the kinetic energy. And so as a result, she found that the distance was 4 times the original value. See, I have a clip about her. It's not really about her science because she was interesting in other rights. Um, but let's just listen to it. It's for your own interest. I think it's interesting. Let's try this quick test. I have a ball that I give a certain velocity. It follows a projectile path. Right here, I give it 35 meters per second at an angle of 30 degrees. And I want to know what is the kinetic energy at the top of the trajectory. Now think about what is the speed at the top of the trajectory and how do I find that? given what I've told you. And then I want to know what is the total amount of energy that this object has at the top of the trajectory. To think back to your projectile motion, remember that if I have what happens to the velocity up here, and how can I find the actual speed at the point, at this point? I'll give you a hint, it's not 35, it's something less than that. We'll do about 10 more seconds. Stop at 155. I'll go on to 2 minutes. Just guess if you're not sure. I'm going to go ahead and stop here. Okay, good. C is right. Uh, the trick here is, or this isn't a trick really, but you want to know the speed here. It only has one component of speed, right? What's the component, the x or the y? It only has the x component because the y component of the speed goes to 0. So at the top of the trajectory, v is equal to vx, which is equal to 35 cosine 30. And that has some value. I'm not sure what it is. Does anybody know right off what it is? Okay, 30.3 meters per second. And then you want to know what is the total energy, 1/2 mv squared. That's the total kinetic energy. It's 1/2 of our mass, which is 0.2 kilograms, times 30.3 squared, and that was equal to 92, right? 92 joules. Yeah, because 30 squared is approximately 900, or 30 squared is 900, and then a tenth of that is 90 joules. Okay, so that's how we calculate our kinetic energy. The work energy theorem, I've already said this, but let's just formalize it, that if I do net work on an object, it changes my energy in some way. And so I can think of this as E final minus E initial. That is what this means, that if I have that delta symbol, that it's the change in my energy, the final minus the initial. So in short, I've said this, but let's just formalize it. If you do positive work on an object, you increase its energy. If you do negative work, you decrease its energy. And that is just that work is equal to delta E. That's what that says. So if work is negative, that causes a decrease. This is a change that is less. It's going to be a negative value. If work is positive, then it is a positive value. I remember the thing I wanted to say earlier. Kinetic energy is always positive, right? Unlike kinetic energy is a scalar quantity, and I know that work was a scalar quantity too, and we said that work could be negative, but kinetic energy is always going to be positive. You should see that in the formula because it's this 1/2 mv squared, and even if you imagine that v could be negative, the negative goes away when you square it, and the mass is never going to be negative. So this kinetic energy is always going to be positive. It is a scalar quantity. I know work is a scalar quantity, but work is the only scalar quantity that we'll ever see that is possibly negative. It's sort of a wonky thing like that. Okay, so let's look at conservative and non-conservative forces. In short, let me just sort of say up front what you need to know. You need to know that conservative forces conserve energy. That is, they don't lose energy. Non-conservative forces do lose energy. You also need to know the examples of conservative and non-conservative forces. The example of a conservative force is a field force, like gravity or electric forces. Those forces never lose energy because they never come into contact. Non-conservative forces are all other forces. Anytime you have a contact force, you lose energy. A great example of a non-conservative force, a force that loses energy, is what? What force takes away energy from a system? Friction. So friction is a good example of a non-conservative force. Let's write all that down. Uh, so conservative forces conserve energy. That is the amount of work done by the force changes the energy by the same amount. And a good example is the gravity force, gravitational force. And non-conservative forces don't conserve energy. Now, as I said, that's sort of a funny way of using that word because we don't usually think of conservative in terms of losing or not losing. So I'm going to write this instead as they don't conserve, or they think, you can think of it as losing energy. So they don't conserve or they lose energy. They take energy away from a system. They're not conserving energy. And friction is as an example. So for non-conservative forces, like friction, we're going to have negative work. Conservative forces, on the other hand, will do positive work. These are going to have negative work because they're losing energy. These are going to have positive work because, well, they're not losing energy. Another thing that you need to know about both of these, and I think that you'll see this as we get deeper into it, is that the work done by conservative forces is path independent. But the work done by non-conservative forces is path dependent. All right, so let's imagine this. I have two folks. They both begin up here. They both have the force due to gravity, a force weight, acting upon them at all points during their fall. One person comes down a slide like this, and then another person just dives headfirst off, into the water or wherever he's going. So both of these have the gravitational force, and the gravitational force does the same amount of work in both cases. Fw does the same amount of work in both cases. You can think of it as work done by gravity is equal to Fw times, or dotted with, the y displacement. So I'll write it as a y. And in both of the cases, they both have the same y displacement. They both start here, and then they both end at a level that's going to be the same, where they enter the water. So the gravitational force does the same amount of work. On the other hand, the frictional force, this guy, has a frictional force acting opposite the motion. The frictional force is path dependent. That means it depends upon the amount of the path that he takes as to amount of work that he does. The work done by the frictional force is equal to the frictional force, Fk, the kinetic frictional force, dotted with the displacement. Not the y displacement, but the total displacement. We'll get into this, and this is where we'll have to begin doing some integrals because we're going to add up all the work that this frictional force does all along the slide. You'll see how that works next time. But let me ask you this question. let's say that this person goes down this slide. I'll label in red. But then let's say that we can change the shape of the slide. Say maybe the slide has that shape. Or maybe we could give it a different shape where it's sort of one of those real curvy slides. I want to know which one does the frictional force do the most work? In which one does Fk do the most work? And we'll call it, red will be A, blue will be B, and then green will be C. Green is C. In which case does the frictional force do the most work? Is it going to be the red slide with some curves in it? Is it going to be the blue slide, which is straight down? Or is it going to be the really curvy green slide? In which case does the frictional force do the most work? All right, I'm going to stop at 38. Okay, it looks like you're sort of split between B and C, which are the two extremes, right? B is our blue slide, C is our green slide. In which case does the frictional force act across the longer displacement? Okay, we're sort of, let's reframe this because we're going to have to think about the total amount of work that's done at each instant. So along the answer here, well, let's just wait, I'll tell you the answer. At each point along the blue slide, the frictional force does a certain amount of work. Let's say it does 1 joule of work up to this point, 2 joules of work up to this point, 3 joules of work up to this point. In order to find the total work, you have to add up all those individual amounts of work. In a similar way, on the green slide, the frictional force acts across each interval. And then in order to add up, or in order to find the total amount of work, you have to add up all the individual amounts of work. At each individual point along the slide, you have to add up, you have to do a summation of all the work that's being done on that slide. So then, which one does the frictional force act over a larger distance? And then that'll tell you which one does the frictional force do the most work. Which one does it act over the longer distance? B or C? It's acting over the larger distance for C. That's right. So the answer here is C. Because it's acting over a longer distance. We'll work some more complicated problems like this, like mathematically, and I think that'll be more apparent. It's sort of new right now. Let me also ask you this question. Will the two people have the same energy just before entering the water? We'll say A, yes, or B, no. Will they have the same amount of energy? This is looking at the person that jumps off and just comes straight down, and then the person that comes down the slide. Any one of the three slides, it doesn't matter. Do they have the same energy, yes or no? Stop at 35, 35. Okay, good. B is right. Which one's going to have more energy? The person that jumps or the person that slides? Obviously, right? You've jumped off like a train. Have you ever jumped off like a train trestle or anything? Or jump from a big cliff into the water? Yeah, you go a lot faster than you do if you go down a slide. Because on a slide, you jump off, you come down, you have a lot of kinetic energy. That kinetic energy is equal to the work that's done by gravity. And that's all that it's equal to. But if you go down a slide, this person has kinetic energy equal to the work done by gravity minus the work done by friction. So the person that comes down the slide, because it has this non-conservative force acting upon it, has lost some energy. We used to skip school and go jump off the train trestle. We would wait until the train started coming at us, and then like right as the train would get close to us, we'd jump off. Ever do that? Is that just a Mississippi thing? Y'all don't do that in Louisiana, do you? You do in West Virginia, right? No. Okay. Um, let's try this. This is a dot product, and then we'll move on to conservation of energy. We've done one before like this, so um, just practice your dot products. You will have to do a dot product on the test. I want to make sure that you know how to do it. Here I give you your initial and your final positions. This is your initial, this is your final position, and this is your force. I want to know the total work that's being done by that force. Your first thing will be to find what is the displacement vector, because I only give you the initial and the final. I'm going to start writing a little bit up here, but continue on working. Work is equal to F dot D. You guys get used to writing vectors in this way if you're not yet. I know we haven't been doing it a whole lot, but you need to get used to writing our vectors with our x, y, and z components. Remember, k is our z direction. Typically, we take out of the board to be the positive z direction. So your first step here is to find the displacement. We've done one similar to this before. So I'm taking the final minus the initial to find the displacement. I subtract my x components, subtract my y components. There's only the one z component. Where is it? Right here. So I keep it negative, so it says R2 minus R1. So this is my displacement vector. Now I take the dot product here. Remember, with the dot product, you only multiply like terms. So don't be freaked out by the FOIL on this, because it would be, I don't know what, 9, 12 terms or whatever. I just multiply these two terms these two terms and these two terms, my I dot I, my J dot J, and my K dot K. So once you do it a couple of times, you just realize that you don't have to go through the whole FOIL. And that's going to be equal to, so what's 4 times 16? 64, is that right? So 640, is that right? I'm right, okay. And then 140 minus, what's that, 720? So the work that's being done is, what is it? 60 joules. Now this was a test question. Notice it was just 10 points. But likely what you'll have is you'll have a more involved question that will start with you doing a dot product. We'll look at some of those next time in class. All right, one more thing before we wrap up for today. You okay on the dot products? Hopefully everybody's okay. You will have to do it, I mean, so make sure that you're capable of that. Let's look at gravitational potential energy, and then next time we'll get into conservation of energy. The work energy theorem. Work changes our energy, and work is equal to force dotted with our displacement. So far we've only talked about kinetic energy, but we did mention potential energy. Potential energy is the energy of an object that has potential for motion. So if I have an object and I hold it some distance from the Earth's surface, it has potential. And in order to unleash that, all I have to do is let it go. And it'll move. It'll go into motion. So it does have potential for motion. When I lift this object up off the ground, I do a certain amount of work. So, for example, let's say that I have this object. I move it from here up to here. I do a certain amount of work. We're going to call this y, delta y. That work is equal to the force that I apply to the object times the y displacement. Um, Now, this force has a magnitude equal to the weight, which is equal to m times g. So the work that I've done there is going to change the energy, and this energy we're going to call potential energy. Because I've now given this object the potential for motion. Potential energy, sometimes you'll see it as PE. We're going to call it, well, we'll call it PE for now. Later, we'll also call it U at some point. And so if you see U written otherwise, that's sort of a more typical term is to write U. But for now, we'll keep it, oh, let's use U. You want to use U? Okay. I use PE in my other class, but it's more standard to use U. So let's just stick with U. So our potential energy is equal to U, and that's equal to the work that's being done by U. So it's equal to this force times the y displacement. That force is m times g. So PE is equal to, or the potential energy is equal to m times g times y. Often you'll see this instead written as U is equal to m times g times h. So if I have an object that's a certain height, the second time, if I have an object that's a certain height from the Earth's surface, it has an energy in joules equal to m times g times h. Tyler? It's a capital U. Yeah. All right. Um, I think I know we have a few minutes. Well, let's do a few clicker questions. Have we done any of these yet? We done which one? Where did we leave off? Do y'all know? Anybody know where we left off? I'm sorry, what? 5-5. This one? Okay. Huh? The book doesn't have it. Did it have this one? Okay, yeah. I'm sorry. I think I just copied it twice accidentally. So But I'll post all of them online as I always do under concept tests. So there are about 6 that are not in your book. Let's try this one. By what factor does the kinetic energy of a car change when its speed is tripled? If I triple V, what happens to the kinetic energy? Remember, my kinetic energy is 1/2 mv squared. So if I triple V, what happens to the energy? All right, we'll stop at 42. 42. Okay, good. D is right. 1/2 mv squared. If I triple this, that makes a factor of 9 over here. Car 1 has twice the mass of car 2, but they have the same kinetic energy. How do their speeds compare? This one's a little tricky to think about. Which one has the bigger speed? Does car 1 or does car 2 have the bigger speed? And car 1 is the bigger of the two cars. Which one has the bigger of the two speeds? Which one's going faster? Car 2. It has the smaller mass but the same energy. So you can get rid of D here. And now we want to ask ourselves, well, gosh, by what ratio do their speeds are they gonna compare? We'll make this our last one. We're doing pretty decent actually. Well, about 2/3 of you. All right, I'm gonna stop at 120, and the answer is B. Uh, if I have twice the energy, that means I have to have a root 2 here because root 2 squared is equal to 2. All right. We'll get to use the bowling ball next time. We're going to get into conservation of energy. But I'll see you on Monday. Have a great weekend.